Okay, we've seen how to create step functions from the Heaviside function. If we can create step functions, then it's not difficult to create functions that have a non-constant linear nature on intervals. For example, we could do something like this, okay, or something like this. Let's look at just a function that's linear from alpha to beta, from some number, from some t coordinate here to some t coordinate here, and goes from 0 to 1 on that interval. How do we write a linear function that does this? Okay, well, and how can we then extend this to a linear function that repeats, let's say, this behavior, so that we get a function that looks like this. For example, we're applying a voltage to a circuit. The voltage increases, drops to 0, increases, drops to 0, increases, drops to 0, periodically. Or we're applying a force to a mechanical system. Okay, we get a little more force, then we let off the force, then we immediately start increasing the force again. So we keep pulsing a force and see what that does to, let's say, some sort of an oscillating system. And you know, the current class hasn't done a lot of physics, so we can't talk too much about systems of that nature except mathematically, but you can still develop an intuition for that sort of thing. Okay, well, so in order to do that, we first have to be able to do this on an interval. Now, how can we multiply a Heaviside function, or the Heaviside function h of t minus alpha minus h of t minus beta, which we've seen over here, gives us a function that's equal to 1 just on this interval and 0 everywhere else. How can we multiply that function by something to give us the linear function? Well, it's actually pretty simple. We know what the slope of this thing is. We know how high it's going to go. We know how long it takes to get there. And in this case, the slope is going to be 1 over beta minus alpha. If we weren't going to 1, if we were going to some other value, well, it would be that value over the beta minus alpha, the time interval, in other words. Okay? So we multiply the Heaviside function, which is always 1, by a linear function with a slope of 1 minus beta minus alpha, this slope, equal to 0 when t equals alpha, and to 1 when t equals beta. Well, these are actually kind of redundant conditions. If it has slope 1 over beta minus alpha and is equal to 0 when t equals alpha, then it's going to be equal to 1 when t equals beta. Or if it has this slope and it's equal to 1 when t equals beta, then it's going to be 0 when t equals alpha. Or if it's equal to 0 when t equals alpha and 1 when t equals beta, it's going to have this slope. So any two of these conditions actually suffice. I'm going to use this condition, the slope, and the fact that it's equal to 0 t equals alpha, and say that, well, if we multiply a function that's got a value of 1 by the slope times t minus alpha, well, you're going to have the slope times t. That's going to give you the right slope. And you're going to have, if t equals alpha, you're going to get 0. So this is going to constitute a linear function which on this interval is equal to 0 when t equals alpha. It's going to have slope, the slope that you need to get up to a value of 1 when t equals beta. So that's one way to do it. There are other ways to think it through. Now we can then we could, by an integration, or actually using tables with shifts and so forth, determine what the Fourier, Laplace transform of this function is. If we then repeat this, we're going to get into a situation that's going to remind us of this. And this is as far as I'm going to go with this idea right now, but that's how we would get a function here. And then I think using this with the techniques and the insights we've gotten from this example, you'll be able to go further with it. And of course, we have this, then we have two functions for every period, one of them with a negative slope, one with a positive slope, so we'd have to set this up for the two different slopes. And in any case, if it's repeating, then we keep shifting whatever number of units and alternately, well, we just keep shifting the function. We end up with a sequence and a Laplace transform that's not too difficult to obtain. Okay. We want to consider then a differential equation. Now this is a very familiar type of differential equation. It's a non-homogeneous second order equation with constant coefficients. We can easily solve the homogeneous equation. And if f of t is a function that we can integrate after we've done the variation of parameters and so forth, or a function whose that gives us a clear idea of what the trial function ought to be so we can use undetermined coefficients, we can solve the non-homogeneous equation, okay, either by undetermined coefficients or variation of parameters. That's not going to work with a step function. You can't write a step function in closed form. You can't do the things with variation of parameters and or undetermined coefficients that we've done with other types of functions. In this case, you're going to need to transform the differential equation, and we've seen how to do that. Transform the differential equation into Laplace transform space, solve the algebraic equation, then bring it back into the real world and get the actual behavior of the functions. Okay, so let's say that f of t is this. And this is just a step function where you're making a step every 4 units, you're stepping one way or the other. So that should be obvious what this function is. It's going to be 1 from t equals 0 to t equals 4. It's going to be 0 from 4 to 8. And then from 8 to 12, it's going to be 1 from 12 to 16, and so forth. And we can write that, of course, in summation notation. Let k go from 0 to infinity, take negative 1 raised to the k. So when k is 0, you get 1. N times h of t minus 4k. Well, if k is 0, that's h of t. So your k equals 0 term will just be your h of t. Your k equals 1 term, you're going to have negative 1 to the k, is going to give you a negative. And h of t minus 4, well, that's this. And you can check that then if k equals 2, you're going to get this. If k equals 3, you're going to get this. Then you understand the pattern. In any case, let's just say you've got that step function, driving a circuit or a mechanical system or whatever. The Laplace transform of this function, as we've seen, is what we've gotten. Now, before we were changing the step every half unit. Now we're changing the step every 4 units. So the negative 1/2 s that we had previously becomes a negative 4s here. Then the Laplace transform of y prime is going to be, well, Laplace transform of y minus y of 0. You remember how to do that, just using a little integration by parts. If you got to use a table, if we're not asking you to do the integration by parts to prove it, it's perfectly okay to use the table. That would be the Laplace transform of y prime. Laplace transform of y double prime is the Laplace transform of y prime minus y prime of 0. And of course, the Laplace transform of y prime is this. And we get what we get. And then we substitute, we get this expression, and that's very straightforward. We substitute this expression for y double prime, this expression for y prime, and of course, L of y for the Laplace transform of y. Okay, so it's substituting, I didn't say it right, but this is substituted for the Laplace transform of y double prime, this for the Laplace transform of y prime, and the linearity of the Laplace transform and everything gives us this equation in a very straightforward manner. Now, what do we do with this equation? Well, we ran out of time and I wasn't able to do it in class. I'm going to go ahead and do it now. We got the Laplace transform of y, and we got 2 Laplace transform of y, and we got the Laplace transform of y. That gives us 4 times the Laplace transform of y. And then we're going to have y prime of 0, 3 y of zeros. They're negative on this side, we're going to add them to the other side, so we're going to get 2y of 0 plus y prime of 0 plus 1 over s times 1 over 1 plus e to the negative 4s. Now, if we know what y of 0 is and what y prime of 0 is, then we're going to get constant numbers here. We divide through by 4, and we get an equation for our Laplace transform of y, and then we inverse transform that to find out our function y, and then we have our solution, okay, or our functions. So, not going to go any further with this because we've got to work a little bit with inverse transforming stuff of this nature, using partial fractions and other techniques. And of course that's where we're going to go next. So, the point is that when we have a system that's driven by a function of this nature, a step function, or maybe one of these sawtooth functions or some other function that we are learning to construct and be able to do next time, we can then Laplace transform the equation, solve for L of y, and then figure out what function we would have to transform to get our L of y. And our L of y in this case would just be all this stuff divided by 4.